Hello everyone, I'm Farad from ECC section, and in today's Tech Talk topic, we are going to talk about the application of Turing numerical inversion of Laplace transform. Let's first see what is numerical inversion of Laplace transforms. In space-time processing, it's necessary to establish 2D space-time systems, model signals, and models. Sometimes the 2D convolutions cannot reflect the relationship of, say, space-time signals and corresponding processing systems. We need CST. Here, CST means continuous space-time systems to process 2D space-time signals. However, CST systems are described by linear 2D partial equations. Generally, it is impossible to get the closed solutions of the RST systems due to the eigenvalues of continuous space systems to be continuous is truly complex space. We had to use the 2D numerical inverse Laplace transform to get the numerical solutions, that is, the space time responses of our RST systems. To our knowledge, through 2D NILT, here NILT means numerical inversion Laplace transforms, has been proposed. This space-time analysis approach of CST systems is still a gap, which involves a vector 2D NILT. This paper will provide the space-time domain analysis for RST systems. We'll also try to simplify the existing 2D NILT based, where the author has ignored the existence condition of 2D NILT. A theorem has been proposed to guarantee the 2D NILT. We provide the derivation of NILT based 2D FFT from integral of 2D ILT. We have not considered the 2D NILT of two variables vector functions. The models of 2D CST systems. Similar to classical 2D continuous systems, 2D RST systems can be expressed three kinds of models. 2D processor model as following. Dou of x to the power t of t comma v by dou of t in the matrix and dou of x to the power v t of v by dou v. Here, matrix can be written as x to the power t of tv, t comma v, x to the power v of t comma v plus u of t comma v, and y of t comma v is equal to x to the power of t comma v and x to the power v of t comma v plus du of t comma v. Here, m of t comma v belongs to R. X is state vector related to the time variable t. N of t comma v belongs to R. X is state vector related to space variable v. Q u of t comma v belongs to R is input vector t. Y of t comma v belongs to R is the output vector. And by calculating all the vectors, we get the output. In all of this paper, we restrain that space variable v doesn't depend on time variability. Suppose that the boundary is x of 0, 0 comma infinity is equal to 0 comma v and x is equal to 0, tv comma take 2D Laplace transform to equation 1 so that we can get the solution in the system T 2D in S and S domain. X to the power T of S1 comma S2, x to the power V of S1 comma S2 in the matrix is equal to matrix of S1 I1 minus A11 minus A12 and minus A21 S2 I2 minus A22 inverse x to the power t of 0 comma 0 and x to the power v of 0 comma 0 plus again a matrix b1 b2 of u of s1 comma s2. Y of s1 comma s2 is equal to matrix c1 c2 whole matrix x to the power t of s1 comma s2 x to the power v of s1 comma s2 plus du of s1 comma s2, and the characteristic polynomial of the first equation is d of s1 comma s2 is equal to determinant of s1 i1 minus a11 a minus a12 minus a21 s2 of i2 minus a22. Substituting 2a into 2b, we can get the input and output equation, which is y of s1 comma s2 is equal to c1 c2 whole matrix of s1 i1 minus a11 minus a12 minus a21 s2 of i2 minus a22 whole inverse again a matrix of x to the power t of 0 comma 0 and x to the power v of 0 comma 0 plus b of b1 b2 and into u of s1 comma s2 plus du of s1 comma s2. Here let's take the 2D Laplace transform to equation 4. We can get the space-time solution y of t comma v. Y of t comma v is equal to L2 inverse of y of s1 comma s2, which is equal to 1 by 2j pi whole to the power 2 c1 plus infinity c2 plus infinity. Integration goes from c1 minus infinity to c1 plus infinity and then c2 double integration of c2 minus infinity to c2 plus infinity y of s1 comma s2 e to the power s1t e to the power s2v ds1 ds2, where minus L denotes the calculation of inverse 2D Laplace transform. The space-time response of the CST system can be obtained by h of t comma v L2 inverse of 1 by v of s1 comma s2, where b is defined by third equation. Different form of 1D continuous systems, the 2D eigen values are not independent and separative. Generally, it is impossible to get closed form solutions of CST systems. Thus, it is necessary to apply NILT to solve equation 5 or equation 6. The Laplace transform of a real valued vector function y of t comma v is given by an integral where 1, 2, SS are complex quantities and 1, 1 S is equal to C plus J omega and 2, 2, 2 of S is equal to C plus J omega are known as the Laplace variables. Y of S1 comma S2 is equal to integral of 0 to infinity double integral of 0 to infinity e to the power minus s1t minus s2v y of t comma v dt dv. This is equation 7. There are two restrictions on y of t comma v that are necessary for the 2D integral to exist. Y of t comma v must be piecewise continuous. Y of t comma v must be of exponential order TV is less than me of t comma v. Where most of the functions of interest in the study of dynamics and control of the CST systems are continuous throughout all the positive time and space. The function y of t comma v, such as a single pulse, has two discontinuities, one at each end, but all the pieces of the function that are attached to discontinuities are continuous. In some of the numerical algorithms, we must select a value of such that the restriction is satisfied. The restriction here in the equation 8 can be concluded into a stability problem. We have the following theorem to guarantee that equation 8 is satisfied. So here is the theorem. Lemma 1. If B satisfied the condition 8, if B of S1 comma 1 is not equal to 0 for R of S1 which is greater than 0, B of j omega 1 comma S2 is not equal to 0 for RE S2 is greater than 0, and all omega belongs to R. The proof of the lemma have been provided in 6 to 7 equations. The proof of theorem 1. Since the adjacency matrix has following relationship with the inverse matrix and characteristics polynomial, here we can see all the matrix calculations which are taking place. And finally, let's, after doing adjacent values, we've got the equation 10. Then let h of s1 comma s2 is equal to 1 by b of s1 comma s2, and taking the inverse 2D Laplace transform to h of s1 comma s2, we have h of t comma v is equal to L2 inverse h of s1 comma s2. Since this equation 12 is Hurwitz stable due to lemma, we have limit t to t comma v is equal to 0 approaches to infinity. Then all the entries of the inverse matrix in equation 10 will converge to 0, which leads to limits y of t comma v, t approaching to infinity, v approaching to infinity is equal to 0, which is less than me to the power sigma t plus v. The inverse transforms for equation 12 is defined by the inversion formula, and here is the inversion formula where C1 and C2 are positive real constants. Numerical inversion algorithms are based on numerically evaluating various equivalent forms of this integral. Vector 2D NILT based on 2D FFT. We begin with the definition of the inverse transform given in equation 14. We can simplify this to the integral by noting this, which is given in the picture, which are complex conjugates. The imaginary terms cancel and the real terms are symmetric about omega 1 is equal to 0 and omega 2 is equal to 0. The integrand RE of y c1 plus j omega 1 comma c2 plus j omega 2 approaches to 0 as omega 1 and omega 2 increase. We can integrate to finite upper frequency of omega 1 and omega 2, which is shown here below. Now we have the derived 2D numerical of Laplace transform based on 2D FFT. In the 15th equation, let omega 1 is equal to 2 pi k1 by m and omega 2 is equal to 2 pi k2 by n, then d omega 1 is equal to 2 pi by m and d omega 2 is equal to 2 pi by m, as well as let nt is equal to 2, so that we can obtain the equation of 2D numerical inversion of Laplace transform as follows. And here is the equation which is being shown here. To be the inverse 2D discrete Fourier transform of y of c1 c1 plus j2 pi k1 comma c2 plus j2 pi k2. Let us take an example of CSC systems. In this section, we provide a stimulation example to illustrate the application of the proposed method in this paper. Let's consider the 2D CST system in one with the parameters as follows. Here we can see in the picture. We have to take a 4 by 4 matrix and a 2 by 2 matrix to solve, and another 2 by 2 matrix. It can be verified that the nominal system is asymptotically stable. Substitute the parameters into the fourth equation and then apply to the 18th equation to calculate the given system output. We obtain the space-time result which is shown in the figure 1. The obtained result also shows that the given CST system is to be stable. In fact, in this example, the changing system unit, we can get a different output. Let us conclude the topic. This paper proposes space-time analysis approach for 2D CST systems. The main difficulty of the space-time analysis lies in the 2D CST systems to be expressed as linear 2D partial equations, and it is difficult for find the closed form of the solutions of the systems. Resort to proposed vector 2D NILT. This paper involves an algorithm for solving linear 2D partial equations in the domain and spacetime domain. A theorem is proposed to guarantee the existence of 2D NILT. The existence problem has been ignored by 8 to 11. The stimulation verifies the proposed approach to be valid. Thank you so much.